In the previous video, we covered the basics of a Swerve drivetrain, including how it functions mechanically and the intuition behind how field-centric drive works. In this video, we're going to dive deeper into the math behind Swerve and explore how these concepts are used in some WPI-lib functions. At its core, Swerve drive is a problem of going from desired motion of the robot to the motions of 4 independently controlled Swerve modules. The first thing I'll cover is sending commands to individual modules. Each of the 4 modules is given a target state, which consists of a target speed and a target angle. We'll discuss later how these target states are actually calculated. One thing to note, however, is that there are technically 2 valid angles to get the wheel to point a certain direction, just with opposite wheel spin directions. This creates a problem, which is that the Swerve module might rotate the long way to reach the target angle. To mitigate this, we can use angle optimization, where Swerve modules select an equivalent angle that results in the least amount of rotation. For example, if the specified target angle was 135 degrees, we could instead rotate 45 degrees in the opposite direction, and then flip the direction that the wheel spins. In general, if the difference between the current and desired angle is more than 90 degrees, we add 180 degrees to the desired angle and flip the wheel spin direction. Just a quick disclaimer, this next part is going to be more math heavy, and it assumes some prior knowledge with trigonometry, vectors, and basic rotational dynamics. Basic linear algebra is also used, but it's not necessary knowledge to understand the underlying concepts. I'll link some videos in the description that cover any prereq knowledge to understand this part of the video. Previously, I explained that in field-centric drive, the driver's input vector is rotated by the robot's heading so that the robot drives in the desired direction. The input vector comes from the controller joystick, where the x and y axes define the desired direction of motion. This input vector is also scaled such that when the controller joystick is pushed down all the way, the robot drives at the maximum allowed speed. With that in mind, if the robot was rotated 90 degrees counterclockwise relative to the field, a command to go forward would result in it driving left. After applying the heading rotation, however, the same command will correctly produce forward motion relative to the field. Mathematically, this can be expressed as a clockwise rotation of the velocity vector by the robot heading. More precisely, this rotation converts the velocity vector from the field coordinate system to the robot coordinate system. Let Vxf and Vyf represent the field relative velocity components given by the driver, and Vxr and Vyr represent the resulting robot relative components. Further, let theta represent the robot heading. This transformation can then be written as the following in terms of the variables that we just defined. These equations are derived from a clockwise vector transformation, and this derivation will be shown in a separate video for those interested. This clockwise transformation can also be represented by the following matrix transformation, but the result is the same, which is a robot relative velocity vector. In WPI-lib, the Swerve drive kinematics class contains a method called from field relative speeds, which performs this transformation directly if we give it the field relative input vector and current robot angle. Now that we have this robot relative vector, we need to use this and the angular velocity of the robot to calculate the individual states or vectors for each module. We can do this using a bit of physics and geometry. When a robot is only moving translationally, the velocity vector for each module is pretty straightforward. However, when it is translating and rotating, we also need to account for the additional velocity caused by rotation. First, we need a formula for the tangential velocity of a rotating object. If you imagine a point on the robot rotating in a circle, its instantaneous velocity is always tangent to the circular path. How do we find out the magnitude of this velocity? Well, we can go back to basic geometry. Consider a circular sector with radius r, angle theta measured in radians, and arc length s. The formula for the full circumference of a circle is c equals 2 pi r, so the arc length of a sector is proportional to its angle. We can see that the 2 pi cancels out, so we're simply left with s equals r theta. Now, to get an equation that connects a linear velocity and angular velocity, we can simply take the derivative with respect to time, which gives us ds dt is equal to r d theta dt, which can be rewritten as v equals r omega, defining omega equals d theta dt, and remembering that the rate of change of the arc length is simply velocity. This formula tells us the magnitude of the tangential velocity at a given radius, which we can use to account for the rotational component of each Swerve module's velocity. Now, to apply this to getting the overall velocity vector for each module, let's look at a visual. Each module has a position vector which is drawn from the center of the chassis to the corresponding module. For simplicity, we'll focus on just one module and label that vector r. Similar to what was mentioned earlier, when the chassis is purely rotating, the instantaneous velocity of the module is tangent to this position vector. We already have an expression for the magnitude of this tangential velocity, so all that's left is determining the direction. Since the position vector is r is equal to rx, ry, a vector perpendicular to this for counterclockwise motion is negative ry, rx. Normalizing this gives us a unit vector that points in the direction tangent to the position vector. Multiplying this unit vector by the tangential speed v equals r omega causes the magnitude of the position vector to cancel out, which simply leaves us with the following, which gives us the rotational velocity vector for each module. Finally, to get the overall velocity vector, we can sum the rotational and translational velocity vectors. However, the way this is implemented in WPI_lib allows us to simply pass in chassis speeds, or Vx, Vy, omega, and instantly get this overall velocity vector. The process we went through to derive this vector can be compressed into one simple matrix. This is pretty much how the two Swerve module states method in WPI_lib ties everything nicely together. To summarize, the process starts with the driver's translational and rotational commands. The translational input is first transformed into the robot's coordinate system using the heading. Then, this robot relative velocity vector is combined with the robot's angular velocity to generate an individual vector or module state for each Swerve module. Finally, this module state is optimized to minimize rotation using the approach outlined at the start of the video. Thanks for watching, and if you'd like to see more stuff like this in the future, make sure to like and subscribe.